This is Algebra 2 at Trig, 2b.5a. We're going to be factoring the sum and the difference of two cubes. When we're factoring, always look for a GCF. We're going to take the GCF, the greatest common factor, out first. Then you would continue to factor if needed. So, for example, we'll look here. And what I notice is that we have a y cubed, a y squared, and a y. We have something in every term. So we're going to pull a y from every one of these terms. We place that y on the outside of the parentheses. If I took that y away from y cubed, that would give us y squared. If I took that away from negative 4y squared, that would give us negative 4y. And if I took the y away from negative 12, we would be left, took it away from negative 12y, we would be left with negative 12. So that was our greatest common factor that all of these terms had. But you still have to be observant that this might be factorable. Notice it has three terms. So looking at our quick notes on the first page, if it has three terms, this could factor into two binomials. So let's see if we can make this factor into two binomials. We're looking for two numbers that multiply to be negative 12 and that are going to add to be negative 4. You can either do this table in your head, which is just fine, or you can write it out. Gives you some organization. You're looking for two numbers that are going to multiply to be negative 12, and the larger number is going to be negative. So 1 and negative 12, 2 and negative 6, 3 and negative 4 are all the ways to multiply to be 12. This is the only way that adds to be negative 4. Now notice that our leading coefficient of the square is a 1. So the shortcut in our parentheses is to drop the positive 2 and the negative 6 right into the parentheses. You don't have to set it up into 4 terms and then factor by grouping. You can just take your two numbers that multiply to be 12 and add to be 4 right into your parentheses. Of course, the first term that makes y squared has to be y times y. You can test the rest of it by saying y times negative 6 and 2 times y. That adds together to be negative 4. And 2 times negative 6 makes negative 12. You can always check every single one of your factoring answers to see if it works for your question. Don't forget to write your GCF in front of the final answer. We look at our next example. Seems a little scary. It has a fifth power on it. So if it has a fifth power, we don't have special rules for multiplying to the fifth power. But that doesn't mean we can't factor this. We can probably turn it into a problem that doesn't have to the fifth power in it. Or we're going to treat it as if it wasn't a fifth power. Here we're going to look at, it has a GCF. I see that g cubed is the smallest exponent. The 3 is the smaller exponent. That means you can take it out of both terms. Notice that we have a 5 here. This number ends in a 0, which means 5 goes into it. 5 goes into 10 and 20 and 30 and 40 and all the way up to 80. So we're going to factor out a 5g cubed from both terms of this. So this is going to become, what's going to be left over? What would be left if I pull the 5 and 3 of the g's away? Would be g squared. And this would be 16. 5 times 16 makes 80. Now you may notice that this is a minus. It's 2 terms. So if you look back at the front of your page, if you have 2 terms, we're going to do the difference of 2 squares. So you could look at the beginning of our question, and you saw that this was a minus, and you considered it having 2 terms, but it wasn't perfect squares. So we had to do something more to it. We couldn't just do the difference of 2 squares right away. We had to look for a GCF, and that turned it into the difference of 2 squares. So to factor this by the difference of 2 squares, we're going to take the square root of the first term and the square root of the last term. And then you're looking for 2 terms that are going to multiply to be a negative. You can test this. G times G makes G squared. G times a positive 4 and G times a negative 4 makes 0 for the middle, and 4 times 4 makes 16. So there we have factored it completely. We're going to move into our special pattern. This is called the sum of 2 cubes. This is called the difference of 2 cubes. Notice that with the cubes, we have sum and difference. But with squares, you can only factor the difference of 2 cubes. We'll experience that a little bit later. So there's a pattern here. Just like it was with the difference of 2 cubes, same type of pattern when it was this difference of 2 squares. We took the square root of each term. So in this case, we're going to take the cubed root of each term. What times what times what makes a cubed? A times A times A makes A cubed. B times B times B makes B cubed. So we've taken the cubed root of both of those terms. Now here comes the pattern. You've got to figure out what can you multiply by to make something cubed. So what would A have to multiply to become A cubed? It would have to be an A squared. So what did we do? We took our term and we squared it for this position every time. The last term, what are we going to have to do to B to make this term? You're going to have a B squared. Now we have to leave space in here because when we multiply and FOIL this in there correctly, in this case that would be called double distribute. If it was a minus, we'd get a 0 term in the middle. But because it's a plus, we can't just have 2 binomials. So what we're going to have to do is change our sign and multiply the 2 together. And I'll show you how that makes this work out. So if we multiply this together, A plus B times a squared minus ab plus b squared. When we factor this, we can check our answer by multiplying it together. This is going to be a cubed, just like we said it would be. This would be negative a squared times b. So our a times our b squared is ab squared. B times a is a positive a squared b. B times negative ab gives us a negative ab squared. And trying to fit this in here still, we got b times b squared gives us b cubed. Barely fits. Notice what's going to happen. We have an a squared b and we have an a squared b. Those would be considered like terms. This is negative, this is positive, they're going to cross out. This is ab squared and ab squared. Those are like terms. This one's positive, this one's negative, they cross off. What do we have left over? A cubed plus b cubed. You can always check every factoring question to see if you get the original problem as we had here. Here's our same, but it's the difference of two cubes. So a minus b. You're going to square the a, change the sign, multiply the two together, and square the b. Notice the last term is always positive. This one matches the original sign. This one is going to be the opposite of the original sign. And this one will always be positive. So that's the pattern of your sum and difference of two cubes. So let's look at numbers that are perfect cubes. What's 1 times 1 times 1? And what's 2 times 2 times 2? Three times 3 times 3 is 27. 64. 125. Now we get a little bit crazier. 36, because that's 6 squared, times 6 is 216. 343. Now this is 64 times 8. That's going to be 512. 9 times 9 times 9. 81 times 9. I know that has to end in a 9. So if I'm not mistaken, 729. And this one, 10 cubed, is going to have 3 zeros. So 10 cubed, 10 squared is 100, and another 10 of them makes 1,000. So these are the numbers that you want to recognize as being cube rootable. We're looking for these types of numbers, and then we can use these special rules for it. Let's take a look at this first one. The leading coefficient is a 1, so that's 1 is a perfect cube. 27 is cube rootable. Take the cube root of 27, we get 3. So since the cubed root, we put a little 3 inside what almost looks like a square root, but we put the 3 there, so it's a cubed root. We're taking the cubed root of w cubed. We're taking the cubed root of 27. You probably won't write this when you're doing your regular work. You'll at least think it. You are welcome to write it. What's the cubed root of this term? What times what makes W cubed? W. What times what makes 27? So now we notice that this is a perfect cube and that's a perfect cube, and we're doing the difference. So we're going to use this pattern here. W minus 3, because the original problem has a minus in it, this has to have the minus in it. The first term is going to be what? W squared. You're going to square your first term. What's your next sign going to be? You're going to switch your sign to a plus. Then we multiply our two terms together. 3W. Then we square our last term. Plus 9. You can multiply that all together if you like to check your work. Let's move into our next one. Is 27 a perfect cube? Yes. Is 125 a perfect cube? Yes. So that means we can take the cubed root of this first term. We can take the cubed root of the last term. So that's going to give us 3x with a plus, and the cubed root of 125 is 5. This is implying that 3 times 3 times 3 made 27, and 5 times 5 times 5 made 125. We took the cubed root of both those terms. What's going to be our first term? It's going to be 3x, but we have to square it. What is 3x being squared? 3 times 3, x times x. You've got to make this a 9. You can't just say 3x and put a square above it. It would have to be 3x with parentheses around it. That's what we're squaring to make 9x squared. Then we change the sign. We multiply the two together, and we square our b term. This trinomial will never be factorable. You never have to worry about factoring that apart. Nothing multiplies to be 9 and adds to be 3. Nothing multiplies to be 25 and adds to be 15. Well, that would have to be 225, right? But it won't be factorable. Never have to worry about that. All right, here's a scary one. We have d to the 5th. We've already learned that we don't do to the 5th powers. So what do you suspect we might need to do? We're going to have to look for a GCF. So I notice that both numbers are even. The best I can pull out of this is a 2. And because it's negative in front, I'm going to pull the negative out with it. So I'm going to pull out a negative 2. And my lower exponent is a square. So I'm going to pull out a d squared. That's going to leave me with some left inside. What's going to be left in this first term? D cubed. 2 d's and 3 d's. When you multiply them together, when you multiply the d's, you add exponents. That makes 5. A negative times a negative is going to make this a positive. What are we going to have left when we take the 2 out of 250? 125. And when we take out 2 of the d's, we've took out all the d's. So there's nothing left. Now, can that go farther? I notice that this is a minus. I know this is a cube with a 1 in front, and 1 is a perfect cube. 125 is a perfect cube. So I should be able to factor this apart using the difference of two cubes. This pattern right there. So I take the cubed root of the first term minus the cubed root of the second term. What's going to go next? D squared. What's my next sign going to be? Plus, change the sign. How do I get my next term? Multiply the two together, so 5D. And how do I get my last term? Square the B term, which in this case is a 5. There it is. All right, let's try our next one, letter D. What do we see here? This is a little bit trickier. All right? We know that we can't have b to the 5th power. We see that they both have b's in it. So we know we're going to pull out our lower exponent, which is a square. So we know we're going to pull out a b squared. 16 is not a perfect cube, so I'm most likely not going to see or work with 16. So what can I turn 16 into? What can I pull out of 16 and turn it into a number that's smaller than 16? Can 16 turn into 8? Yeah. By dividing by 2. That works great. What if I divided this crazy number by 2? 343. Cut each number in half. Hey, that worked out great. So that seems to be our answer. There would be a consideration. Could you take 686 and factor the entire 16 out of it? And the answer is no. It comes into a decimal. But 686 divided by 2 is 343. So we're just going to pull a 2 out of it. So that's our GCF, 2b squared. So what are we going to have left inside? Two times what is going to make 16? B cubed, because when you add those exponents together, you get to the 5th power. Nice work. 2 times what is going to make 686? 343. And it's just 343. There are no b's, because that, with this b squared, that would give us a total of 686b squared. We did these numbers on purpose. Now we have an 8, which is a perfect cube. Now we have a 343, which is a perfect cube. So we're going to take the cubed root of this first term, which is 2b, plus the cubed root of 343, which is 7. We're going to square our first term, which is going to be what?
4b squared.
4b squared. What sign are we going to use?
Wait, how's it minus 4b squared?
Multiply the two together is going to give us 14b. And then we're going to square the 7 to give us 49. Now the tricky part is often this term right here, 4b squared. Where do we get 4b squared? We took our first term, which was 2b, and we squared 2b. So when you're squaring the entire 2b, that's going to square the 2, and that's going to square the b. So 2 squared is 4, b squared, 4b squared. And remember, this will never be factorable. You don't have to worry about coming up with that crazy factor. it almost looks like, right? It almost looks like you can take the square root of this and take the square root of that. And maybe their product is half of this. But it's not. 2 and 7 is exactly that. It doesn't make half of it. All right, that is our notes on the sum and difference of two cubes. We have our pattern, and we use them up here. What we're going to look at next is what if we're working with 4 terms? Look at this. This is h cubed. Cubed, h squared, h, and this doesn't have another term at the very end. So notice that this does not have a GCF in it. In the past, we may have had a variable in every term like we had up here. We had a variable in every term. Here, we don't have that variable in every term, so we can't just get rid of the cube that way. But this is 4 terms, and in our notes, we read earlier that if it is 4 terms, we could factor by grouping. It might be factorable. So let's see if we can make factor by grouping work here. Sometimes when you see a polynomial with 4 terms, you can factor by grouping. And the key thing that I'm trying to show you is that it is sometimes. Not every time can you factor by grouping, but sometimes you can. So let's find out if this can be factored by grouping. So we circle our first term. You guys have all factored by grouping before. You've got to figure out what can divide into 27 and 45. What number goes into both of those? But a 9. Your smaller exponent is a 2, so it's going to be h squared. That's going to leave us 3h and a positive 5. You bring down your sign, which is a minus. We look at 3h minus 5, and there's nothing we can factor out of that. But we have to put a number out here. So we're just going to factor a 1 out, or if you want to call it a negative 1. So negative 1 times something makes negative 3h. Negative 1 times something makes negative 5. Notice inside the parentheses here, they are exactly the same. They have to be exactly the same. If they're not exactly the same, then you can't factor it by grouping. We're going to experience that in the future. So this is going to be 9h squared minus 1, and then 3h plus 5. You do not put a square on 3h plus 5. You're essentially factoring out your common factor on either side of the minus. You're factoring that part out, and you're left with the 9h squared and the negative 1. Now, being observant, do notice that you can take the square root of both sides of these, so this is the difference of two squares. You have to continue. You have to factor it completely. So take the square root of your first term is 3h. Take the square root of your last term would be 1. So 3h plus 1. If you multiplied, FOILed that together, you would get 9h squared minus 1. Don't forget to bring down your 3h plus 5. We never worked with that any further. So this gets factored into those two terms, and this one comes down here. Something to point out from the previous problem, you can't forget, which I didn't write it down, but you can't forget to bring down your GCF, your greatest common factor. What you pulled out has to be part of your answer. Must be part of your answer. just like here, you have to factor it completely. You've got to look to see if you can take the square root of both sides. So let's come over here to this one. We're going to circle the first group, circle the second group. I can only factor out a y squared. That leaves me y minus 3 I bring down my sign. (16 times 16, or 16 plus 16 is 32, and another 16 gives me 48. So 48 is divisible by 16. I can factor out a 16, and that's going to leave me a y minus 3. And what's inside the parentheses is exactly the same. So here I'm going to have y squared plus 16 and y minus 3. The y minus 3 does not get a square on it. Now, this is a common mistake. A lot of people are going to think that you can still factor this apart. But checking my work, this was truly a plus in between here. There's nothing that this factors into. It is not y plus 4, y plus 4. That won't work. Try to FOIL that together. You will not get a 0 in the middle. That's the best you can do. So, the flip side. Got a little bit more. Of course. So, what we're used to x squared. Okay, we're used to working with x squared, and when we do that, we come over here and we have x times x, because that makes x squared. If we have x to the 4th power, we're going to treat it just like x squared. But instead of putting x and x in our parentheses, we're going to place x squared and x squared in our parentheses. So when we multiply it, FOIL that together, we're still going to get x to the 4th. When we're working with x to the 6th, what are our two terms going to have to be that multiply each other to make x to the 6th? X cubed and x cubed. They're going to multiply together to be x to the 6th. So let's come on down here. These all have crazy GCFs with them. But what we're going to first see is that I can pull a 3 out of these, an m squared out of these. So that's going to leave me m to the 10th power plus 18m to the 5th power plus, that would leave me, that goes in there once with 2 left over, so that's 17. Now, we would think before that we could not factor this. We can't do to the 10th power. We don't have a rule for the 10th power. But notice how the 10 and the 5 are half of each other. Just like when we worked with a problem, that would be m squared plus 18m plus 17. How would we factor that? This we wouldn't be too concerned about. What multiplies to be 17? 17 and 1. What multiplies to be m? M and m. Plus and plus. So you get m squared. You get 1 plus 17 times 17. So this becomes 18m in the middle. And you get m squared, and you get to 17 on the end. Well, we're going to do the same thing here, but instead of using m and m, what times what is going to make 10? When we add the exponents together, what's going to make 10? 5 and 5 is going to make 10. 17 and 1 is going to multiply to be 1m to the 5th, and 17m to the 5th make 18m to the 5th. So we treat that just like it was an m squared problem. This here is the difference of two squares. 4g squared minus 25 and 4g squared plus 25, because this is the difference of two perfect squares. This part is a perfect square again. 2g minus 5, 2g plus 5. But this is not a perfect square, so we have to leave it not factored. And we'll come over to our next one. We have our tens. We'll pull the tens out. Now we look at this, we get scared that it's to the fourth power, but what if that was actually an x squared? Would you feel more comfortable factoring something like that? And we would say the difference of two squares. We would treat that as x times x to make x squared. 1 times 1, a positive and a negative. Negative and a positive make 0 in the middle. So this is the difference of two squares. Well, we're going to treat this the same way, but we're going to have x squared and x squared, because that multiplies together, you add exponents, to be x to the fourth power. We would still have 1 and 1, because we'll have positive 1 and negative that makes 0 in the middle, and 1 times 1 makes 1. Notice this is the difference of two squares again. So we have to break this one down, and it would be x times x, 1 times 1, a plus and a minus. This is x squared plus 1. And don't forget, your GCF always has to be first. This one cannot factor. Nothing breaks that down. A lot of people think that that's going to turn into x plus 1, x plus 1. But notice when you check your work, you get a positive 1x. You get another positive 1x. And this makes 1. So you actually get 2x there in the middle. So this doesn't work. This is not that. We'll pick up on these on the next video when we talk about solving. None of these were solving. These were all factoring. So we've done all the factoring.